Let's do this thing. All right. So BPE stands for boiling point elevation, and FPD stands for freezing point depression. Now, what can help is, even before we talk about the chemistry of all that, just think of what it means, boiling point elevation. It means I add salt, for instance, to water, and it boils at an elevated or higher temperature. Freezing point depression, what does that mean? It means I add salt to water, and it freezes at a depressed temperature. Okay? So with that in mind. So this is Raoult's law, and actually I'm going to walk you through a way to get to another form of Raoult's law. But according to Raoult's law, you can have, and remember how this works, we're going to use the same convention. This is the pure stuff. Anytime you see that not, think pure. Okay? And this is the solution. Solution meaning it has a solvent plus a solute. So basically the pressure of the solution, the solvent in the solution, is going to be only equal to the mole fraction of the solvent times what it would be if it was pure. Okay, well, if you only have a binary system, binary meaning two, you have the solvent and the solute. If you add up their mole fractions, and you only have two things, the mole fractions added together should be equal to 1. We can rearrange then the mole fraction of the solvent is equal to 1 minus the mole fraction of the solute. There's only two things there. So now what I'm going to go do is substitute that quantity in Raoult's law for the mole fraction of the solvent. There's too many S's, far too many S's, because we have solvent, solute, and solution, 3 S's by my count. So this is getting closer to another form of Raoult's law. Okay, so the pressure of the solvent that has a solute dissolved into it is equal to 1 minus the mole fraction of the solute times the pressure of the solvent when it's pure. Well, we can distribute this P naught through that quantity, okay, and it looks like this. Just a little bit of algebra. Okay, and then we can rearrange it to look like this, where actually then this is the other form of Raoult's law. Delta P, the change in vapor pressure. Okay, vapor pressure lowering. It's always vapor pressure lowering when you add some solute to a solvent. So delta P is the pressure of the solvent in solution minus the pressure of the solvent when it's in its pure state, is equal to negative the mole fraction of the solute, too many S's, times the pressure of the solvent in its pure state. Solute, solvent. Ugh. So that could be helpful. Okay, and we're leading up to the freezing point depression, boiling point elevation laws. Equations, I guess I should say. Freezing point depression, boiling point elevation equations that kind of look like this a little bit. All right, so here we go. We looked at this before, and just to kind of remind you, we're going to go with this convention where the blue one is how the substance behaves in its pure state. The pink line is how the substance behaves to which the solvent to which a solute has been added. So when we talk about vapor pressure lowering, that's really what it has going on. Vapor pressure lowering, for instance, to me, kind of, I'll pick on green. You know, if we pick any given temperature, let's pick the boiling point temperature, we can go along that temperature and we can see the lowering of the equilibrium vapor pressure. We talked about that before. But now we're going to focus on the boiling point elevation and freezing point depression. So any phase diagram, whether it has basically a pure substance and a solution, you can pick out the boiling point temperatures and the normal boiling point and the normal melting point temperatures by, dun, 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 like is seen here, picking on regular pressure. Regular pressure walking around here is 1 atmosphere, 760 millimeters of mercury. Okay, So you pick on that pressure, and you go along and you see where it coincides with your pressure temperature curves. For instance, this would be going from what, a solid to a liquid, so that's melting point, or and freezing point, same thing, melting point, freezing point. And this one right here is going from a liquid to a gas, so that's boiling point. So if we compare the pure stuff to the impure stuff, for instance, this right here is boiling point elevation. The pink one is the thing that has a solute added to it, solvent with a solute. The blue is the pure solvent. Okay, and this right here is freezing point depression. FPD and BPE. Okay? So that's what it looks like on the graph, on the pressure temperature phase diagram. Here's what it looks like mathematically. Okay, blue box alert, blue box alert. So these are on your sheets you're going to get tomorrow. You just need to know how to use them. So the increase in boiling point temperature, the boiling point elevation, that's the change in temperature of the boiling point. It's all the same thing. Boiling point elevation is equal to some constant K. And I'll put both of these up here. Times the molality of the, and it's, let me make sure it's on the, yep, too many S's. It's the molality of the solute, the thing that's there in lesser amount. Okay? So that's boiling point elevation. Freezing point depression is similar. Okay, freezing point depression is delta TFP, okay, is equal to negative K FP, molality again of the solute. Now this slide, I think it says on the next slide, but just let me go ahead and tell you that these Ks, these are, you look them up, or you can calculate them if you have the molality of the solute and freezing point depression or the boiling point elevation. But usually these are in a table, usually. Cool. The next slide tries to kind of clean this up a little bit, but freezing point depression, it's always final minus initial, and since it's a depression, can you see where your delta T FPs are always going to be negative? Okay? Freezing point depression. It's T minus T naught, where T naught is the pure stuff, and it freezes at a lower temperature. Boiling point elevations, your delta T BP is always going to be positive. Okay? So, yeah, the KBP and the KFP. The KBP is the boiling point elevation constant. The KFP is the freezing point depression constant. Okay, again, you look them up, and it's going to be specific for a solvent, for the thing that's freezing or melting, the solvent. Okay. I can't remember if I added that thing at the bottom of the slide. All right. So you look up KFP or KBP, or like you see from the equation, if you know the depression or elevation and you know the molality of the solute, you can go ahead and calculate it yourself if you need. So here's the deal. You look that up on a table, and there'll be a constant, both boiling point elevation, freezing point depression for water. There'll be one for benzene. There'll be one for chloroform. There'll be one for you name it. So here's the deal, though. You look it up, it's for a particular solvent, the thing that's doing the boiling, the freezing, or the melting, or the condensation. But it's independent of what you sprinkled in to your solvent. That's the solvent, right? It does not depend on what your solute is. Granted, it depends on the molality of your solute, because that's what's in the equation, little m of your solute. And this kind of comes full circle, and there's no vocab, but this would be a great vocab question on your test. The Okay, anytime somebody says that's a colligative property of matter, then that just means that it depends only on amount, but not what that matter is. Colligative property. I think we had a slide earlier. So both those effects in boiling point elevation, freezing point depression depends only on the number of particles, not what the solute is. So here's some K values. So these would all be solvents, right? These are all solvents. Kind of nasty solvent. So this is when they normally freeze. This table you might need to use for your homework. But if you need it for a test, I will give it to you. And with regard to the freezing point depression constant, here are the freezing point depression constants per molal of solute. Don't care what the solute is, but per molal of solute for each of those solvents. I think you've got one of your last homework questions to assign today to bring to your test basically says kind of which one is most affected by throw in 1 molal. So what it's saying is, for instance, if I were to have 1 molal of anything, salt. Let's make a 1 molal solution in acetic acid, okay, where I'm just putting salt in there. Then can you see where it would freeze, instead of 16.6, it would freeze at 16.6 minus 3.90. Freezing point depression per 1 molal. That's how that works. And what I started to say is, can you see where phenol, if instead of acetic acid, if phenol is your solvent of choice, dang, for every 1 molal of solute, whether it's salt or whatever it is, whatever your solute is, for every 1 molal, it's going to depress the freezing point temperature 7.27 degrees Celsius. So that's how that works. So for those same substances, here is the temperature they normally boil at if they're pure, and then the next column is the boiling point elevation constant. So, you know, for a given substance, the freezing point depression constant and the boiling point elevation constant are not necessarily the same. So units of all of these, I'll put all these up here. These are all possible ways of units for the freezing point depression constant and the boiling point elevation constant. It's just temperature, degrees Celsius per molal. Okay. So the thing about our textbook is they make the freezing point depression constants positive, and then like you have on your test, the negative is associated with the equation. In some cases, some textbooks, general chemistry textbooks, will make the equation positive and make the negative sign associated with the constant itself. So just to kind of give you a heads up with that. Okay, so here we go again. You guys don't have this one again? Okay, so I'm hoping, you know, the picture's worth 1,000 words. I'm hoping you all see the boiling point elevation and the freezing point depression kind of here. This is good because we again revisit what normal freezing and boiling point temperatures are on the phase diagram. Okay, so we said that the vapor pressure lowering was a result of those little solute particles kind of running interference. And I actually showed a video where the equilibrium vapor pressure and the headspace above a solution that has solute in it, the solute basically kind of tamper down the ability of those solvent particles to go from their liquid to their vapor stage. Okay, they kind of run interference. And that's kind of a little bit what happens when something is less likely to freeze if it is in solution versus its pure state. So what this is trying to do, and I'll maybe kind of emphasize, is down here, down here, south of that, okay? Basically, the beautiful crystals are pure, okay? And they're nice, and they do their solid thing. Basically, looks like it's a crystalline lattice structure, some sort of salt. And up here, this basically is a mixture. And you can see instead of having nice solid crystals, basically we still see a liquid up here. Okay? And so this figure will help show you that, I think. So this figure, kind of going from left to right, the black balls, or the first beaker actually, is the sol is in its pure state. Okay? And then this one right here is actually, the red balls are the solute that's been added to the solvent, and they kind of run an interference for a crystallizing act. So it's less likely to come out of solution. That's the way I think of it. All right, so let's do a couple problems. Okay, so what is the freezing point of a benzene solution that boils at 82.0 degrees Celsius? You're like, I have no idea. What temperature, oh, well, you don't know what temperature benzene usually boils at. Could you find in the information I gave you in one of those little tables the temperature at which benzene usually boils at? Is it in the table?
It tells us.
Oh, good. So if I keep going, it tells us everything. Okay, so boiling point elevation we can pick up by difference there, the delta T BP. Okay, so the way we're going to work this basically is to calculate our delta T BP, look up on a table what the KBP is for benzene, and then come up with the molality of whatever's in there. We don't care. And then we're going to apply it to the freezing point. Okay. So it tells us that benzene usually freezes at 5.5 degrees Celsius. The depressed temperature is what we're going to be after. So here we go. The KBP and the KFP, we look it up for benzene. It's kind of a classic sort of problem. So let's knock these out. Okay, this is what I said. Use the boiling point elevation to find the molality of the solute, which we don't care what it is. Then use that molality to come up with the freezing point depression. And then apply that delta TFP, that freezing point depression, to what it should usually freeze at. Goodness gracious. And this is the line that we got the information on the previous slide from. All right, so here we go. The delta TBP, okay, it's always the final minus initial. In this case, the final is the stuff that, the elevated temperature. From that, we subtract the temperature it would be if it was pure, boil at if it was pure. So make sure on your test to show all of your work. It'd be heck to lose a point here and there, just not showing this work. Of course, we round according to decimals. 1 decimal, since we're subtracting. We don't do as much subtracting as we do multiplying and dividing. But that's our boiling point elevation. And then we know our KBP, so if we kind of rearrange the boiling point elevation equation to solve for molality, it looks like this. So the molality of the solute is equal to delta TBP, which we just came up with, divided by KBP, which is from the table. So it looks like this. Don't forget your units. So 1.9 degrees Celsius divided by, that KBP is 2.53 degrees Celsius per molal. Notice the beauty of this is your degrees Celsius will cancel, and you'll be left with 1 over molal in the denominator, which is the same as molal in the numerator. Okay, rounded to 2 significant figures. The molality of our solute, which we never will know what it is, but its molality in terms of moles of solute per kilogram of solvent is 0.75, 0.75 molal. So now we're going to use that forward in our freezing point depression equation. So a freezing point depression equation looks like this with a negative sign. And that's the way it is on your sheet for tomorrow. The delta TFP, that's what we're solving for this time. So we pick up the KFP from the chart, okay? So the freezing point depression constant for benzene is negative 2.15 degrees Celsius per molal of solute, per molal, per 1 molal solute. And then the molal we came up with was 0.75 molal. So our molals cancel, and we're left with units of degrees Celsius, which is great. Rounded to two significant figures. Okay, we end up with a freezing point depression of negative 3.8 degrees Celsius. So delta FP is TFP minus T naught FP. Okay. And we are solving for this depressed temperature without the naught, the depressed temperature right there. So we could rearrange this and say what? The depressed temperature is equal to delta T plus T naught. All right. So the depressed temperature T is equal to negative 3.8 degrees Celsius. That's the depression, plus 5.5 degrees Celsius. That was the temperature it usually freezes at. Again, we're adding here, so we go with decimals. So round to 1 decimal. So your depressed temperature is 1.7 degrees Celsius. That works. Okay. This one, just so we're all on the same page, and after this, I don't think we'll go on to the Van Hoft thing. We may or may not, the last part after assignment. But this problem we're going to do right now is actually listed here. Number 8, using molar mass, or using freezing point depression to calculate molar mass. So here's how you do it. And I think if I was doing this, I would make I'm going to go ahead and make a little drawing here. This is how I work these. A solution of 5.0 grams of lauryl alcohol in basically, 100 grams of benzene. So does this make sense? So can you see where our benzene is our solvent? To me, to work these, I have to identify the solvent in the solute. It makes my life easier. 0.100 kilograms. Okay, and I think I'm gonna, and you can too if you want to. I'm gonna abbreviate lauryl alcohol as LA. If that's okay with you. So 5.00 grams of LA. Lauryl alcohol is added, and that is our solute. Cool. And then, let's see, a solution, blah, 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 freezes at 4.1 degrees Celsius. You think it's a depressed temperature? I do. So this thing freezes. I'm going to go ahead and put it without a knot. TFP, freezing point of this solution, is 4.1 degrees Celsius. So before I forget, I'm going to go ahead, and the end says, what is the molar mass of LA? What is the molar mass of our solute? Question mark, molar mass of LA. What helps me is to go ahead and to set up what the units of molar mass are. that would be grams of LA per 1 mole of LA. That's what the molar mass is. Does that make sense? Grams of LA per 1 mole of LA. That is our target. So there's more information given here. Oops. So we can look up the freezing point depression constant. So KFP for benzene, which I clearly said is the solvent. We'll look that up on the next page. And we also need to know what T naught FP, what benzene usually freezes at. And that's also over here. So here we go. Looks like a freezing point constant 5.12. That would be degrees Celsius per molal, and that's the molal of the solute. And it normally freezes at at 5.53. So, you know, bird's eye view of this, yeah, we do have some depression going on. So the strategy looks like this. Okay. We have enough information to use delta TFP, freezing point depression, is equal to negative KFP times the molality of the solute. Okay. We can get this, right, from these temperatures. Delta T, we have this from the table. Okay, we can get the molality of the solute. And then my next suggestion, and again, there will be one of these on your test, and you can have practice at homework. Once you have the molality of the solute, let me go ahead and do it this way. This is my target right here, molar mass of the solute. Once I have molality, molality, okay, that is, in this case, moles of lauryl alcohol to 1 kilogram of benzene. Because benzene's my solvent. Okay, once I have molality, I can go ahead and I'm going to show you how, with this other information that's given, we can do it. Okay, so the first part is just finding the molality of the lauryl alcohol. We can knock out the delta T is T minus T naught. So the depressed temperature is 4.1 degrees Celsius. The T naught is 5.53 degrees Celsius. Rounding it to only 1 decimal, because that's all we know in the depressed temperature. The delta TFP is negative 1.4 degrees Celsius. And then I can plug that in up here, or rearrange this to get to my molality. So if I rearrange the freezing point depression equation, of course the molality is equal to the delta TFP divided by negative KFP, which in this case it looks like this. Our delta T, our freezing point depression, was negative 1.4 degrees Celsius, divided by, from the table, the freezing point constant depression, negative 5.12 degrees Celsius per molal. Again, make sure you use all your units, because units will give you confidence that you set it up right. We'll have units of molal left, rounding it to 2 significant figures. The molality is 0.27. So over here, I'm going to go ahead and put 27 moles of lauryl alcohol per 1 kilogram of benzene. That's actually on the next slide. I've unpacked what molal means. So now the way I think of this is, now I'm going back to my raw data. This is why I drew a picture. So that's the molality of my solute. This is the picture I drew. This was the original information given. Okay? So what I'm going to do is basically scale up those moles to this mass that was given. I didn't have 1 kilogram of benzene, I had 0.100 kilograms of benzene. With that in mind, what number of moles of solute did I have then? So I can take my 0.100 kilograms of benzene, which is what I had, and then multiply it by the molality, which is what I came up with. Kilograms of benzene cancel, and we're left with moles of solute, moles of lauryl alcohol. Rounding it to 2 significant figures, the moles I have is 0.027, not so surprising. Move decimal place, right? 0.027 moles of lauryl alcohol. So, here's how we can now get to finally the molar mass of lauryl alcohol. So we have moles per 5 grams. Those moles were in these 5 grams. These grams were equal to those moles. What is molar mass? It's grams per mole. And that's it. That's just it. Molar mass, grams per mole. So the last thing you're going to see here is basically the 5.00 grams divided by the 0.027 moles. Rounding to 2 significant figures. That is the grams per mole of this solute. And that's it. That's the molar mass. MMM. It's a classic. So these 3, not 1370, that kind of snuck in there. So just 69, 71, and 72 will be due tomorrow. You know, and whether you do them or not, it's kind of up to you. I will make them available under talk sharing. So as long as you don't like just Xerox copy what I have up there, you know, you're welcome to kind of use it at your discretion. Let's take a look at those right quick. Maybe. And I posted these hints before I came to class again. I'm getting with it. Okay, so this might look familiar. Okay, this basically is what we just did. It gives you the mass of an unknown, and it says that your solvent, right, is benzene. And it gives that mass, and it says that benzene usually freezes at 5.53 degrees Celsius, but in this case it froze at a depressed temperature of 4.92 degrees Celsius, and you're supposed to come up with the molar mass of the unknown. So I can't remember what my hints were. But I kind of went back and forth a little bit. Again, make sure you're kind of get your wits about you. Benzene is clearly the solvent. An unknown solute is added. So in orange here it says you would look up for benzene, the freezing point depression constant. Actually, it's the same one we just used, isn't it? And you could get the delta freezing point depression from the T and the T naught were given up above. You can knock out the molality, and then just like what we did before, okay. Oh. So what we did before was then, after we have the molality, okay, that will be, Your molality will be here, some sort of moles of unknown per kilogram of benzene. That's by definition what molality is. Then I have you revisiting the information given. You were given the mass of the solvent. The benzene is 75.22 grams. The only thing is, since it's not kilograms, you have to scale it up this way. Add one more factor. That will give you the moles of solute. And then last but not least, all you need to do is, I always have to concentrate, molar mass is grams per mole. So basically you're going to take those grams and divide it by these moles to get the molar mass. That's it. Skip this one. If you read it a few times like I have to, you'll see that benzene is the solute this time, and cyclohexane, I drew a little picture of cyclohexane. It's actually a ring sort of structure, but instead of having alternating single and double bonds, it's what we call saturated with hydrogen. It's actually got 2 hydrogens on each carbon. Okay, so that is our solvent, cyclohexane. It asks what is the value for the freezing point depression constant. So it doesn't give it for cyclohexane. You have to calculate it. Usually it's KFP is given. But in this case, they go ahead and they give you the, can you get to, like it says in orange here, you can get to the molality of the benzene, right? Knowing the mass. So you have to use the mass and get to moles, okay? And then scale up, that's moles per kilogram of solvent. That's the molality of benzene. You'll plug that in here, and you'll know delta TFP because that was given in the problem, and you'll solve for KFP this time. Or look it up on the internet. And then my hint for, this is where I kind of said, my hint for the last part of the problem is just which one would be better, benzene or cyclohexane to use as a, calculate the freezing, to calculate the molar mass of an unknown solute. And to me, it kind of, which one ever has the greatest depression, which one has the highest KFP, is what I thought. But, and then one more. Okay, finally we have solvent is the water. Water's the solvent. In this case, they're sprinkling a little bit of sugar in there. That's going to be your solute. And they say that not at 760 millimeters of mercury, but at a lower atmospheric pressure, and actually you are not going to use that 749.2 millimeters of mercury. You won't use that. They just say at that particular pressure, it's supposed to boil at 99.60 degrees Celsius. And they say the target at that pressure is actually 100.00 degrees Celsius. Okay? So then actually you have enough to go ahead and knock out boiling point elevation, your desired delta TBP from those temperatures. And then your delta TBP is equal to your boiling point elevation constant you get from the table times the molality of your sugar, which is your solute. Okay, solve for molality. But then the problem is, kind of goes back to what we worked problems earlier in Unit 1, where you have to get from molality to percent. Because that's what the problem says. What's the percent sugar, not what's the molality of the sugar. So what I would do, once you have the molality, what makes sense to me is base it on a 1 kilogram of water. Because molality, by definition, is moles of sucrose, in this case, per 1 kilogram of water. And work from there and get it to weight percent sucrose. It's all good. So yeah, I think I'm going to hold off the Van Hoft equation. We might look real quickly at that on Friday before we start on Unit 2. But it's not on your test, so I'm not going to worry about it this time. Okay. So